Hi there, this is Jacob Nash, and in this video we'll be going over finding volumes using the disk washer method. Hmm. So, what does this mean? So in the last video, hopefully you watched it, or you're at least aware of cross sections. Instead of building shapes throughout, we are going to now spin a shape around a certain axis. So that means that this time, um, we will get a circle, where last time we used sometimes semicircles, squares, or triangles to determine a volume of a certain shape or a certain shape, basically, um, 3D shape. But this time we are going to actually use discs or washers, and a disc means it's just a circle, basically, and if it's a washer, it means that it has a hole in the middle. And the reason why that would happen is if the way that the shape is formed by the graph, there's a gap. So if you spin it around an axis and there's a missing space, it will result in that. You can also do a cylinder shell, so you can make it a 3D shape, but that's in the next lesson. So right now we're only talking about if it's going to be a 2D washer or disc. So for it to be a disc or washer, it needs to be sorry, I'm trying to turn on the laser thing. It's kind of glitching out. Perpendicular to the axis or line that we're using. So it might say spin it around the y-axis, spin it around the x-axis, but it could also say spin it around y equals 1 or something like that. But it has to be perpendicular. If it's parallel, then that gets into what we'll do in the next video. Um, and like I already said, if it's going to be a washer if there's a gap. So here's an example. So it's kind of hard to visually draw, so that's why it's good to have this example here. So in this case, we're spinning around the x-axis, and yes, the cuts are perpendicular to the x-axis. So it has to be perpendicular to whatever you're spinning around. So since it's the x-axis, it should be vertical cuts. And we get almost small cylinders, but in this case, these are really discs. Um, and yeah, if we make a cross section, it's a 2D disc, but we get many cylinders, and we need to have obviously like usual infinity um of these for it to be exact, because otherwise we do get some slight over or underestimations. Um, okay. Now there are two possibilities of how you can find the volume using the integral, but they're the exact same except for one has x and one has y, depending on what axis you're going around. But we're basically going to do, remember how last time we had Rx for radius in the formula? Remember, the reason why we have that is because the radius is not always the same, because depending on what part of this graph you're on, the radius will change size, so it's really a function. So we have big Rx minus little rx. Now, what does that mean? Well, in this case, you see that there's the big radius here. It starts from here and it goes to this. So in this example, these are the two graphs that we were told about, two functions that we were told about, and then we're trying to find the volume of the enclosure. So we go from all the way over here, the furthest. This is the big radius, and this is a small radius, because when we're creating the disk, there's really two circles. Or sorry, when we're creating a washer, there's two circles. And this would be a washer since there's a gap right here. See this um little part right here? Because it's really going to end up being a rectangle, but there's this part where there's nothing because we only care about this. So there's really two circles whenever there's a uh if you have a washer, you have two circles. You have the inner circle and the outer circle. So this is a little radius, and then the big radius includes the little radius, but it also goes all the way back. So that's what that means. So you subtract those two radii, and we're going to look at why that is in a second. Uh, shoot. Okay, that annotation thing's a little annoying. So here's why. So if we want the area of this washer, how would you find the area of something that's like that, like a donut? How? Well, it's going to be the same as if it was filled in, except for you have to subtract the small part. So that's what we're doing. We're doing the full area minus the hollow area, which is the reason why we have the little r, the radi because it's the area of the big thing minus the small circle, and then we get what's remaining. Um, and then we just import that into here. So for this example, it's saying it we're spinning around the x-axis, and then these are the two curves. So here are the two curves, and we're trying to find the volume of this little leaf shape thing. And so we make a perpendicular cut to what we're spinning around, which is the x-axis. And there you go. That's what shape it creates. That's best thing I can do to try to make it look 3D. Um, I know this might seem a little bit confusing, really just because it's hard to visualize. But you have to just kind of just go with it. Like that's what it's going to be like. Um, so then we move over here. How do we know what the big radius is? Well, the big radius is going to be from the center to the edge, and the edge is this function. So it ends up being that because this distance from the x-axis to here is a y value, and every function is equivalent to that y value. So that's why it ends up being that. So always what the radii are just one of the functions, but you just figure out what it is just by looking. That's why it's important to draw. Then the small radius, which that should be little rx. Apologize for that. That's going to just be from um here to here, and that gets us to this x squared. Now we just plug it into here, and it's pi r squared, really pi r x squared. We can factor out this pi, and the zero is gone from the thing. But you would just find antiderivative as usual. I'm not including that because that's not what we're talking about in this video. So the steps, trying to reiterate, you definitely want to sketch because it makes it easier for you to figure out which is which means you would want to remember how to sketch your average functions that are common. And it doesn't have to be exact unless you have a professor that requires it to be exact, but it just has to generally look like what it is. Um, then you figure out what big Rx is and big R or little Rx or Ry, depending on what you're spinning around. And then you just do what I did. So this is a different example, but this time we are going to see what it's like for spinning around the y-axis. Well, this time we have to make it perpendicular to the y, so it ends up being horizontal. Because once again, anytime we're using disk or washer method, it's perpendicular. So same thing. So this time, what is little or big Ry? You go from the y-axis all the way to as far as the shape goes. It ends here. This is the x equals 8 graph, so it's just 8. Then the little r starts here and then it ends here. So um y equals 2 or y equals x to the 2/3, but since whenever you do something y like ry, you have to change it to x equals something. So we just switch, we get x by itself, so it's ends up being that. That's something important. Whenever you're doing ry or anything when it's relating to the y direction, you have to make it x equals something because instead now we're at the horizontal distance. That's why. So now we plug it in here, and it's the same thing. Now, what if you're not doing it around an actual axis, just a specific line? What if we were spinning around y equals 6? Well, the only thing that changes is that you'll have to make sure that you think about that when you're figuring out what your x and little rx are. So big Rx, we start here and then we go to however far it goes. Okay, it ends here. What is this distance? It is 6. Then we go here. What is this distance? So here's where it can get a little bit tricky. We at least know that this distance up to here is x to 2/3 because that's what this graph is. So if the full thing is 6 and this little part is x to 2/3, then you have to, it's just going to subtract that. So full distance minus partial gets you the other part. So it's 6 minus x to 2/3. By the way, anytime you have something like this, you're going to see it in both parts. So it's a 6. So I see a 6 both here. So it's going to include. So then you just plug it in. So, not that hard. Just get a little bit of practice with that. There you go.